Okay, so here we go. So the students think that the drag force is proportional to the square of the speed. So they come up with this. Fd equals some constant times v squared, where c is a constant, using the relationship to derive an expression relating the terminal speed, vt, to the mass. Shh, guys, please. So what is terminal speed? This is a thing that comes up on a lot of these tests. So what should we be looking for when we reach terminal speed? Sure, we got this. Good. The drag force has to cancel out the force of gravity, which means your net force is 0, right? Cool? So, for part A, it's just our drag force has got to be big enough to cancel out our force of gravity. So cv squared equals mg. Solve for v, and you get mg over c square rootified. Cool? So that was it for part A. Any problems there? Okay. Let's see. Part B. So the students collect some data. It says, assuming the functional relationship for drag force above, assuming this, use the grid below to plot a linear graph as a function of m to verify the relationship. So it's telling you that our horizontal axis is going to be mass. And so the question is, what goes here to create a linear relationship? Okay, well, it looks like if I do v squared, then I get mg over c, right? So if this is my y value and this is my x value, then this ought to be my slope, right? There were a couple of you guys that were asking about that yesterday. Is everybody okay with how I did that? Yeah?
I get that, but like, why do you have to have it squared? Like, why couldn't you just leave it as the square root?
Gotcha. So you
for the masses it gives you.
Because then you'd have to put the square root of them on your x-axis.
Oh, and it tells you that you have to use them.
Yes.
Okay.
So and usually it doesn't specify,
Yeah.
but here it does for whatever reason. So does that make sense, you guys, or no? Everybody's good, yes? Okay, and also I realized I was sloppy here. This should be VT, right? Terminal velocity that we're talking about. Good? All right, so use the extra row of your graph to figure out what VT squared is. Clear? And then plot your data. Any problems with that? All right, if you plot your data, you should get a nice line that goes through 0. Everybody cool with that?
Wait, really? Is that on the rubric, Mr. Hacker, that they allow the square root of m versus velocity of time to also be?
Oh, does it? Oh, okay.
Yeah.
That's interesting. Okay. Weird, because it's labeled on the thing, but okay. So is everybody good? Problems? Going once, twice. Guys in back, are we good? Yes? All right. So the next thing you had to do, it says use your graph to calculate c. So what you want to do is find the slope. When I found my slope, I got 222.2. So as long as you end up somewhere in that neighborhood, you should be good. And then remember, your slope, according to this, our slope is g over c, right? Which means that c is g over our slope. Follow? What's wrong? Sure?
Yeah, Patrick doesn't. Hubert thinks Sarah's cool. Yeah, I'd say that. That's mean. He doesn't think Sarah's enough to go to a movie with, so. Oh.
Yeah, we just spiraled out. This got personal really quick. Sarah, I'm sorry. The Keever's me. All right. Okay, so is everybody cool with what I'm doing here? So find your C. It's going to be 9.8 over whatever your slope was, and it gives you a number, right? Please, this is huge, you guys. Make sure you include units on it. And I had to take a minute and kind of figure out what the units were. So it took a minute to figure out what the units of my slope was. and then divide it out, right? So like g is meters per second squared, right? My slope, well, it's terminal velocity squared over mass. So terminal velocity is meters squared per second squared times mass, right? And simplify that, and you end up getting kilograms per meter. Oh, sorry. Cool. Sorry about my wonky fraction bar. Everybody good? Yeah.
Maybe I messed something up, but is it really supposed to go through the origin? Or...
Mine did.
Oh, alright, I guess I messed something up.
And again, you guys, I'm sorry, I'm like racing to do all the, because I've got these 3 practice tests, so I haven't had time to always check my answers, so.
All of your points are like the box side. It was shifted point 2
You look high. Oh wait, you plotted velocity. You gotta plot velocity squared.
Oh.
Cool. Alright, everybody good?
Is there someone in your closet?
No, somebody probably put something on a shelf that fell. I think we're good.
I don't believe you.
Go look if you want, but I think we're good. Alright,
It's still moving.
Students somehow got locked in there.
yeah, the car just fell off the shelf. Hey! Hi, Mr. McGuire! There's
all okay here?
ghost. There's a ghost in the closet.
Really not.
Startled me. I'm scared of ghosts. All right. Yeah, that was fast. All right. Sorry, all these papers. All right. So is everybody good with our calculation of C? Guys, can we cool the side conversations? All right, thank you. Goodness. All right. So the next chunk says a particular stack of filters with mass m is dropped from rest and reaches a speed very close to terminal speed by the time it has fallen a vertical distance y. And then it wants you to sketch a graph. They made this sound way more complicated than it is. Look, your thing is going to fall and it's going to approach terminal velocity, right?
Yep.
So there's your asymptote. There's your graph. All right? And then you need to pick some time. I did a rotten job drawing this. Let me draw that a little better. Why are you being dumb? There we go. VT. Dot, 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 dot. Here's your graph. And then you just need to identify a point T at which you're basically at that terminal velocity. Cool? It's a weird thing, though, because there isn't a point at which you reach the terminal velocity, right? Because it's an asymptote. Okay? So, everybody good? Okay, part 2. Suppose you had a graph like this, and you wanted to find the value of y. In other words, the distance that it falls before reaching terminal velocity. So what's the relationship between this graph and the distance fallen? Integrate it, right? So acceptable answers would be to say that y is, that's a y, the integral from 0 to t of v of t with respect to t, with respect to t, or you could just write, find the area under the curve between 0 and t. Cool? Do make sure that you specify your bounds that you're going from 0 to t. Cool? All right. Part D, determine an expression for the approximate amount of mechanical energy dissipated, delta E, due to air resistance during the time the stack falls a distance bigger than that y. That's important because that means it's already reached its terminal velocity, right? Does that make sense? So, the idea is, if it has fallen a distance y, that means that at the top of this, all of my energy is GPE, right? And at the bottom of that distance, all of my energy is KE. And since I've fallen a distance greater than capital Y, I've reached my terminal velocity. So how do I find the energy dissipated?
What does that mean?
Dissipated means lost.
KE minus the
So we just need to find the change, right? So you just subtract mgy minus 1/2 mvt squared. And you're done. Did I oversimplify that? Yeah, that's it.
Wouldn't it be final minus initial? So KE
Let's see, how does it
minus
say? It says the amount of mechanical energy. So to me, that doesn't indicate a direction. I mean, you're obviously losing energy. How much did you lose? My guess is that it would be okay either way. All right, good, you guys? Everybody happy? All right. All right, let's see, number 2. Oh yeah, projectiles. All right, so what do we got? 2010, number 2. So we got a bowling ball with a mass of 6 kilograms. It's released from rest from the top of a slanted roof that's 4 meters long and angled at 30 degrees. So here's your ramp. 4 meters long. Since this is 30 degrees, you can very quickly figure out that this is going to be 2 meters. Here's our bowling ball. The problem tells you that the rotational of a bowling ball is 2/5 mr squared. It rolls without slipping. Part A, this is big, you guys. So usually when we make free body diagrams, all we care about is the direction and magnitude of the forces. But here, it says on the figure below, and it gives you this little drawing of a ramp and a ball. It says draw and label the forces, not components, acting on the ball at their points of application as it rolls along the roof. All right? So what's the first force I should draw? Gravity. Where on the ball should I draw that force of gravity? From the center of mass. Very good. Gosh, my board needs to be calibrated. So there's my mg. All right, what else? Okay, I heard friction and I heard normal force. Let's do friction first. Where's the force of friction going to occur? At the contact point, right? Which way does it go? Up or down?
Up.
Up. Are you sure? It's accelerating down the ramp.
Yeah, so we're showing.
It's resisting it from sliding, right? So that force of friction is up the hill. Cool? One other force. What do you got? Normal force. It should be perpendicular to the surface. Where's the point of application? At the point of contact again. I drew that way too long. Yes.
So if it was rolling, I mean, is it rolling?
It is rolling, yes. Because it says it rolls without slipping.
But it doesn't matter, friction is still pointing up.
Correct.
Okay.
So how is, so then let's talk about that then. What's the force that's making it go down the hill? The parallel component of gravity, right? So technically, there's a perpendicular component and a parallel component of gravity, and that parallel component of gravity has to be winning, right? Follow? Any problems? Once? Twice? Sold? Justin, can that wait? Thank you. All right, part B. Calculate the force due to friction acting on the ball as it rolls along the roof. If you need to draw anything else, blah, 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 blah. Okay, so to do parts B and C, I think there are 2 paths that you can use to do this. Okay? So to do part B, you can either use conservation of energy to find the velocity at the bottom, then find your acceleration, then use net force equals net force to find the force of friction. Or you can set up a net torque equals net torque equation and find your force of friction directly. Okay? Which one of those 2 methods makes more sort of intuitive sense to you guys? You find net force using conservation of energy or net torque? Net torque? Okay. Let's do it that way. I think you guys are probably... All right, so... I think there's value in understanding both ways of doing this. So, let me do it this way. All right, so let's write a net torque equals net torque equation. So, net torque equals net torque. So, According to my drawing here, if I choose this as my pivot point, what force is going to produce torque? Friction. Okay? So my force of friction times what's the length of my lever arm, you guys? The radius of the ball, right? Do you guys agree that's my force of, or my torque from friction? Okay, that's got to equal I alpha. I is 2/5 mr squared. And in a minute, we're going to, most of what we're interested in here is linear values, right? It wants linear velocity and blah, 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 blah. So let's replace alpha with A over R. Cool? So if you simplify this, you find that the force of friction is 2/5 of ma. So that's equation number 1. Any problems with it? All right. So now, let's also do a net force equals net force equation. Okay? So, my net force is going to be comprised of friction working against the motion. And what I just did, you shouldn't do on your test. Because remember, it says if you need to add anything to your drawing, do it separate. Okay? So I'm being a little sloppy here. So there's Fg parallel pulling down the hill, force of friction pulling up the hill, right? Follow? So Fg parallel is mg, let me do this. So continuing there. So you get, oh shoot. So we get mg sine theta minus our force of friction. So that's our net force equals what? Ma, right? So I've got 2 equations and 2 unknowns. What are my 2 unknowns? Acceleration and friction, right? So now I can find those 2 things. Follow? Do I need to go through the algebra for how I resolved these 2 equations? Okay, so if you do this, your force of friction ends up being mg over 7. You know your mass, so plug in your numbers. You end up getting 8.4 newtons. And then the acceleration is going to be what? 5/2 the force of friction over the mass. So if you find your acceleration, you end up getting 3.5 meters a second squared. Cool?
Yep.
All right, so that was one of the ways of doing part B. Yes?
Okay, I just had a quick question. This might be super dumb. So,
Wait, Justin, will you stop, please? I already asked you to do that later. Thank you. I didn't say anything when you fired it the first time.
so like, with like something that's rolling, I thought we like didn't include the friction because it's like kind of like rotating at that spot.
Not at all a dumb question. So the force of friction is a force acting on the object. The time when you don't need to worry about it is when we're looking at work. Okay, remember, work is force times displacement. And at that point, there's no displacement. Yeah. Clear? All right. Everybody good with that? All right. Okay, so now part C, it wants the linear speed of the center of mass. Well, let's see. At this point, we know our VI, we know our acceleration, we know our displacement's 4 meters, so you can find VF, right? Clear? All right, now, I'm not going to run through it, but if you wanted to do it the other way, you could use conservation of energy to find the velocity of the ball at the bottom. Now you know your VI, your VF, and your displacement, so you can find your acceleration. Then do net force equals net force to find the force of friction, and that also works. I don't know that one way is any easier than the other. I would say pick the way that's the most intuitive to you. Follow? All right. C, calculate the linear speed. Oh, we just did that. Everybody cool up to C? D, sorry. So if you do part C, the velocity when it gets to the bottom ends up being, written on one of these pieces of paper, 5.3 meters a second. Good? All right. D, a wagon containing a box as it rests on the ground below the roof so the ball falls a vertical distance of blah, 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 blah. Calculate the horizontal speed of the wagon immediately after the ball lands in it. So what concept should we be thinking about here, you guys? Conservation of momentum. Now here's the weird thing on this. When the ball lands in the cart, the ball actually has velocity this way, right? So there are two components to that, right? There's a horizontal velocity and a vertical velocity.
Yep.
Talk to me. How should I deal with that? You got an idea, Zach?
Your vertical velocity doesn't actually matter here
Can you tell me why the vertical velocity doesn't matter?
because it's perpendicular to motion. Or motion.
Okay, yeah.
Yeah.
So all of the cart's motion is going to be horizontal, right? So where does the vertical momentum go? To the ground. There's an external force from the normal force pushing up, taking away that vertical motion. Cool? So, you can find your Vx up at the top, right? We found that the velocity at the bottom of the ramp was 5.3 meters a second, right? We know that this angle is 30 degrees, so the Vx is 5.3 cosine 30. And that gives you like 4.58 meters a second. So that's the horizontal velocity of the ball as it hits. Let me pause there for a minute. Did that make sense? Everybody good? Good? Sarah, you good? You sure? Okay. That wasn't me yelling at you for talking. I was making sure you were good. All right. So now it's just conservation of momentum, right? So the mass of the ball initially times the velocity of the ball horizontally plus the cart is 0. That's got to equal the mass of the ball plus the mass of the cart times its final velocity and solve. And you end up getting 1.53 meters a second. Velocity of the cart and ball system final is 1.53 meters a second. Cool? Questions? Problems? Concerns? Anything? All right, the dreaded tow rope problem.
This was the one that took.
Yeah, this one's tricky. This one is really tricky. The graph at the bottom was the thing that really, because to do the graph at the bottom, you kind of had to go back and reevaluate stuff with this new function. All right, so here we go. So for problem number 3, here's what you're told. It says a skier of mass m is pulled up a hill by a rope as shown above. The magnitude of the acceleration of the skier as a function of time can be modeled by these equations. So the acceleration is a max times the sine of pi little t over period. Okay? And we're only going you're going until you get to the period. Okay? And then your acceleration is just 0 after that. Make sense? All right, so I kind of took a minute to think about what was happening during that time. So let's find the acceleration after 0 seconds. What would that be? Let's see. If I put 0 in, sine of 0 is 0, right? So your starting acceleration is 0. Follow? All right, let's find the acceleration at the end of t, at the end of the period. Well, that's am times the sine of, the t's cancel and you get pi. So what's the sine of pi, you guys? Also 0. Huh. Oh, so that must mean that my acceleration graph as a function of time looks like this, right? Where this is the period. That's a crappy drawing, but do you see what I mean?
Yep.
Yep.
That way.
Okay, now please be careful. It's probably worth your while to take a second and think about your drawing. Here's your skier. What forces are acting on the skier? Well, there's the force of tension from the rope and gravity. Right? So it should be true that MA equals tension minus mg sine theta. Follow? All right, so now that we've established all of that, part A, derive an expression for the velocity of the skier as a function of time during the acceleration. Assume the skier starts from rest. So, how do I get from here to acceleration, you guys?
To velocity.
Or yes, how do I get from here to velocity, right?
Take the integral.
Take the integral. So this took me a little thinking. So here's the deal. Our velocity should be the integral of our acceleration with respect to time, right? So that's the integral of am sine pi t over period with respect to time. So integral of sine is, what, negative cosine? Right? But I'm going to have to do chain rule, right? Am I right? Because derivative of cosine is negative sine, is that right?
Yeah, but
Yeah.
sine.
This should be negative cosine. I think.
What's wrong, Josh?
Nothing.
You sure?
I'm tired.
So, okay, so you understand why?
Yeah.
So, you're right?
Yep.
All right. So I'm going to have negative am cosine of pi t over period.
You
So if
just-
I...
You said the derivative of sine was negative cosine.
Oh, I'm sorry, I meant integral. Sorry, I misspoke. My bad. Okay, so everybody good up to there? All right, am I done?
No.
Why not? Because when I take the derivative of this mess, I'm going to have to multiply by pi over period, right? So to undo that, I need t over pi, right? Now am I done? Yeah, you got to do plus c. All right, so this, I almost made this mistake. So my starting velocity is 0, right? My starting velocity is 0. So check it out, you guys. If you plug 0 into this for my time, does it give you 0? It doesn't, does it? So you've got to tack on a plus c to ensure that at time 0 your velocity is 0.
Could you just plug in a negative AMT over pi?
I think you actually need a positive,
Oh yeah, because it's, yeah.
right?
Yep.
So if you solve, you find out that your c is amt over pi. So my velocity at time t is negative amt over pi cosine pi t over period plus this mess. amt over pi. There you go. Oh, ah!
Sorry.
No, my bad. You got it? Sorry about that. Okay, everybody good up to there?
Yeah.
It's totally weirded me out here. Like this time is not being as well spent as it should be, but nobody's saying anything. So we're going to keep going. Let's see. So there's our expression for velocity as a function of time. Cool? B, derive an expression for the work done by the net force on the skier from rest until terminal speed is reached. Ugh.
Can we skip that one?
No. We cannot. So it's actually not too bad. Okay, so check it out. Wait, what are we trying to find? Yes. Okay, so what is this? This is part B. So we want to find the work done by what? By the rope. Determine the magnitude of the force exerted by the rope on the skier at terminal speed.
No, because
Shoot, I'm doing the same thing I did yesterday. I'm now questioning my answer here.
Can't you just do work exchange with data description?
No, that would be network. We don't know our distance. Shoot. I could have sworn that I checked this answer though when I did this last night. Between my play practice and going to my son's musical. All right, give me 1 second. Josh was checking the answer. I want to make sure that my answer is right. If not, I got to redo this.
What musical is your son?
Sorry? It was the student staff Shakespeare thing on Tuesday.
It says you could have used kinematics or
Is that the answer? I look real quick, do you mind? I'm sorry. I'm sorry, you guys. Thank you.
Mr. Hacker, what musical is your son?
No, they had like the choir concert,
Oh,
like
okay.
second grade. What do we got? Number 3. Work done by the net force. Oh, I'm reading the wrong problem. I'm sorry. My bad. We're good. Oh, wait. No, that's still... No, I don't agree with their answer. Can I see that again? I think they made the same mistake I did. I'm sorry, you guys. I did this last night, and I checked the answer, and now I don't agree with it. Let's see. It says for a correct solution of the velocity. So I just found the change in kinetic energy, but that would give you the work done by the net force, and it doesn't want that. It wants the work done by the net force. So I'm dumb, man. Okay. Sorry, guys. I'm back on board. Sorry for the delay. All right, so I apparently can't read is what caused that delay there. All right, the problem wants the work done by the net force. Okay, so here are your choices. Option 1. This is the not good option. The work done by the net force should be the integral of the net force with respect to position. Okay, so net force is this, right? mt minus mg sine theta. We found an expression for our tension. So anyway, it gets ugly.
yeah.
All right? If you can avoid calculus, do. I will tell you, they love this on the AP test. I see it all over the place. Net work is change in kinetic energy. And the problem wants to know, what's the net work done? So, to do part B, I'm going to do this. My net work is the change in kinetic energy. That's KE final minus KE initial, right? What's the initial kinetic energy, you guys?
Negative K.
It's KE final, right? Sorry, initial kinetic energy is 0. Final is some number, right?
Yeah.
Oh, well that's 1/2 the mass times the terminal velocity squared. Didn't we just write an expression for the terminal velocity in part A?
I can't remember. It was so long.
I'm sorry, Justin.
I have a very poor training.
Oh, we didn't find it yet, but we can find it. So how do I find my terminal velocity?
Set lowercase t equals capital.
Yeah, set lowercase t equals a capital T. That's exactly right. Cool. So Vt equals the velocity at time t, which is,
2a.
so if you solve that, it gives you 2 t a max over pi. So that's our terminal velocity. So plug that in up here and it gives you your work. Yeah.
Network thing with, this kind of confused me. Is how am I doing no network like this? Kinetic, there's no change in kinetic energy. Kinetic energy is the same here as it is up here.
Because the work that you're doing is done by gravity.
Okay. But I'm still not doing any work, any net work there.
Correct. You're doing work to change the total energy, but you're not doing net work to change the kinetic energy.
This is kind of weird.
Yeah, I hear ya. Anthony.
Can you just go back? Like, so if you have for the velocity equation,
This guy?
yeah, I'm curious, what is the A like related to? Because if it's like relating to the thing, isn't it, when it's at its vertical, what's it called?
The max.
The fastest it's going,
Terminal velocity?
yeah, the terminal velocity, isn't there no acceleration, so wouldn't that be zero?
This is a max. It's the maximum acceleration.
It's just the equation.
So it's like a fixed value. I think it's given to you in the equation as like a variable you can use. So there's some maximum acceleration. It's a fixed number. Does that make sense? All right, everybody good? I'm sorry about I got tangled up here. I read the problem wrong. So, everybody good? Jacob?
How do we get the C? So I just got lost there.
You got to plug 0 in for t, and make sure that this whole mess equals 0, because you know at time 0 your velocity has to be 0.
Gotcha. Thank you.
Follow?
Yep.
All right. Okay, everybody up to speed? All right, so that is that. Part C says determine the magnitude of the force exerted by the rope on the skier at terminal speed. So we've already done this question once on this test already, right? At terminal speed, you need your net force to be 0, right? So that means the force of tension from the rope has got to be mg sine theta. So that's all you got to do there for part C. Good? All right, part D, derive an expression for the total impulse imparted to the skier during the acceleration. What's impulse?
Change in momentum.
Change in momentum. So mass times change in velocity, right?
Yeah.
So D, impulse is change in momentum. That's mass times change in velocity. That's mass times our terminal velocity, which is mass times 2t times a max over pi. Cool? All right, so finally, now we got to graph these things. Part E says, suppose the magnitude of the acceleration is instead based on this other model, where blah, 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 blah. On the axes below, sketch a graph of the original one and the other one. So let's do the original one first. So it labels mg sine theta. And what we're trying to graph is the tension force, not the net force. Okay, so this really took me a minute to kind of wrap my head around. Okay, because the idea is we know that net force is mg sine, no it isn't, sorry. We know that net force is tension minus, tension minus mg sine theta. Right? So that means tension is net force plus mg sine theta, right? Which is mass times our acceleration function. So here it's m times a max sine of, what is it, pi t over t? Plus mg sine theta, right? Cool? So at time 0, if the acceleration is 0, what does the force of the rope have to be? In other words, where does my graph begin? Does it begin down here at 0? No, it's got to start here, right? Because the tension has to cancel out the mg sine theta to make your net force 0, right? Good? And then it's going to go up to mg sine theta plus m a max, right? At time t, we know our acceleration is back to 0. So there's your graph. Follow? Everybody good? All right. Then, now we got to compare that with this other graph. So for the second one, it's this. Our net force is now mass times acceleration, but we've got a new model for acceleration. So it's mass times A max e to the negative pi t over 2t. So that's the net force plus mg sine theta. Follow or no? Okay, so at time 0, what does this all give me?
Plus
If time is 0, you're going to get e to the 0. What's that?
1. So
1. So you get ma max
plus
plus mg sine theta. So my graph has to start up here at mg sine theta plus ma max, right? Cool? Now, as t gets bigger and bigger and bigger, e to the negative pi t is going to go to 0, right? So as t goes to infinity, this mess goes to 0, and you're just going to end up with mg sine theta. Okay? So mg sine theta is an asymptote there. Cool? All right. Questions? Felt like I was talking to myself for an hour there. Okay. So here is